that as my introduction. That actually is the intro to the rock group The Who. Pinball Wizard. Fun thing to play on the guitar. Alright, so we're going to get started on 4.6 today. So we're going to continue talking about limits, but we're going to look at a few more special situations. We're going to look at what happens to a function that has asymptotes, either vertical asymptotes or horizontal asymptotes or even oblique asymptotes. So to begin with, I'm going to review what an asymptote is and how to go about finding one. In general, a rational function is just a ratio of polynomials where the denominator contains a polynomial of a degree of at least 1. So in general, it looks like this. Okay, P over Q, it's a ratio where P and Q are polynomials. And you have to remember we've talked about polynomials. Polynomials are sums and differences of whole number powers of x. So let me give you a couple of examples. F of x is equal to, all you got to do is just put a polynomial on top. That's good. And put a polynomial on bottom. So that's a good example right there. Okay. Another example would be something like this. You could just have a number on top. A number, just by itself, is really understood to be 7x to the 0. So that's considered a polynomial. And then you can put anything you want to on the bottom as a polynomial. That is another example of a rational function. Okay. Also, you could have something like this. You could have just something like x minus 1 over x plus 1, even something like that. That's a polynomial because it's sums and differences of whole number powers of x. Now, what you can't have is you can't have something like this, x squared minus x plus 1 over 2. Okay, that's not a polynomial because what you have to have is the degree of the denominator has to be at least 1. So you have to at least have an x in the denominator. So that doesn't count right there. Okay, so here's what you do. A vertical asymptote occurs on a rational function where the reduced form is undefined. This occurs when the denominator is equal to 0. And the key thing is the reduced form, because there's times where you'll have a factor cancel out, and that doesn't give you a vertical asymptote. It gives you what's called a whole. So really all we got to do on these rational functions on here is just figure out what makes the reduced form of the polynomial undefined. You can do this in your head a lot of times. So really it's just setting the denominator equal to 0 and solving that equation, okay, which you can do in your head most of the time. So that's x equals 1. That would be the equation of the vertical asymptote, okay? Now I'm going to pull up my calculator because I want to show you what really happens on an asymptote and why the function behaves the way it does. So I'm going to put this in the calculator. I've got 1 divided by x minus 1. Whoops, not like that. X minus 1. Notice that I'm putting the denominator in parentheses. You got to do that. And then I'm just going to do a window. I'm just going to do a standard window. Zoom 6. Okay, there we have it. So you're going to see this break in the graph at 1. And you'll also see, if I go to my table of values, well, you see we have an error at 1. That's the calculator's way of telling us that we're undefined. So what happens on this, with your graphing calculator, if we're close to this asymptote, we'll be looking at this in a little bit here, but if you traced a number, real close to that asymptote, then typically what happens is the number either gets real big or real small. You can see if I'm just a little bit bigger than 1, then y is already way up to 100. So that's the way the arithmetic works. Basically what happens on what I just did is this. If I plugged in 1.01 into this function, I would get 1 over 0.01. Well, why do you get such a big number? Well, the reason's simple. This is 1 over 1/100th. And remember, if you divide fractions, well, what do you really do? You multiply by the reciprocal. So that's really how the calculator is getting 100. So anytime you take a number divided by something very, very small, what happens is this thing gets real big. So that's why vertical asymptotes, why graphs behave the way that they do. Okay, so that's a good thing to know. All right, the next one, well, it looks like the denominator factors. So what I'm going to do on this one is we need to figure out what makes the denominator 0 just by factoring. So I'm going to draw out two parentheses. My first term is x, so I got x and x. I got numbers that multiply to give 12. You don't have to go through all this. It depends on how much skill you have developed at this point in time with your factoring. These are all possible things that multiply to give 12, but we need to make these add up to 4, so you can make a 2 and 6 add up to a 4 if you have a plus 6 and a minus like that. Okay, so what this would do then is we would just set each factor equal to 0, and you're more than welcome to solve this in your head. Add 2 to both sides, that'll give x equals 2. Subtract 6 from both sides, you get x equals negative 6. So the equations of these two vertical asymptotes are x equals negative 6 and x equals 2. Okay, visually you can pretty well always tell you're right on this. I'm not going to keep doing these over and over again on a calculator, but a calculator is a great tool for understanding and checking. It makes everything very visual. So I'm going to go ahead and put this one in and show you a couple things that happen on this. And I'm going to do this in a standard window. Okay, so get that put in, just graph it. So you're going to see that you have this asymptote at 2, you have that break in the graph, and at negative 6 you also have that break in the graph. And again, what happens, the graph either goes way up or it goes way down whenever you're at a vertical asymptote. You get big, really big numbers or really small numbers when you get closer and closer to the value of a vertical asymptote. And of course, don't forget, look at your table. The two places where there are errors are where you're going to have vertical asymptotes on there. So the calculator can kind of help you visually see what's going on the problem. Okay, the next one is a little different situation that you have to be really careful about. This one, again, you want to reduce the rational function first. Okay, if you factor x squared minus 16, remember that we call this a difference of two squares. And this is a special type of factoring problem that shows up a lot. So you draw two parentheses, and the first term is going to be x times x. And then the last term, you're going to use 4 times 4. It's a perfect square, so you use the same number. Then you have a plus and a minus. You FOIL that out, you'll kind of see how the inner and outer terms cancel out. So what happens is you get this. This thing right here goes away. That's really 1 right there. So this is what we call a hole. It's not a vertical asymptote because it's gone away. The vertical asymptote is going to be the factor that's left over. So your vertical asymptote, you solve this equation, so you get x equals 4. And you only have one vertical asymptote on this, even though this function is undefined at 2 places. This function is undefined at negative 4 and 4. Okay, but the negative 4 becomes what we call a hole in the graph, and the x equals 4 is a vertical asymptote. So this one's also worth looking at on the graphing calculator. So I'm going to throw this in real quick. I got x plus 4, divide by, then I'll put in x squared minus 16. All right, just do a standard window, and let me show you what I mean by that hole. So you're going to see the vertical asymptote at 4. You don't really see that hole unless you really zoomed in on the graph. But there is a hole right there. And one thing that you can see on here, if I go to my table, see you got an error in 2 places. You got an error at negative 4 because the function's undefined, and you got one at 4. So that's your hole. That's your vertical asymptote. The one that cancels out is not the vertical asymptote. So you have to reduce the rational function before you figure out the vertical asymptote. Okay, all right, so that'll take care of that. That should be review, hopefully, from pre-calculus, college algebra type of classes. Now we're going to get into the calculus. So we're going to look at these and graph these things with the help of our graphing calculator. So I'm going to put in 1 over x minus 2. Always be sure that you have, if there's more than one term in the numerator or denominator, they have to be in parentheses. Okay, I'll just set this window up like it is, or you can do a standard window, negative 8 to 8, And then the y's are also going negative 8 to 8, like my graph is doing. And then I'll graph that, and then we're going to just draw a few things. Okay, so first of all, what is the vertical asymptote? Okay, well, figure out what makes the denominator 0. The vertical asymptote is x equals 2. So typically when you graph this, you just go draw a dashed vertical line that represents the vertical asymptote. It's not really a part of the function. It's not a part of its graph, but it's an important part of the function. And then what I'm going to do is just look at my table, maybe get see if there's any good, nice whole number values. I always like to kind of do that. So I see a few of them here. I see 1, negative 1. I also see 0 and negative a half. And then I'm also seeing 3, 1. Like that. And then I see like 4 and 1/2 like that. That's just to get a little bit of accuracy is all. And then the rest of it we're just going to sketch. So what's going to happen, when you got a vertical asymptote, the graph does not touch the asymptote, it just gets close to it. And it either goes up or down. And we're going to also learn that these graphs, if you have what's called a horizontal asymptote, the graph levels off. So you want to go ahead and draw this function like that. And then that's a pretty accurate graph of what that function looks like. Now, I've already filled out the table, just to save a little bit of time. We've gone over how to do that. Just use your trace feature. So just a quick reminder, if you type trace 1.9, then you get the negative 10 like that. So what you're going to find happens on this is we're just getting closer and closer to 2. This right here is your vertical asymptote. That is your vertical asymptote right there. So the function's undefined. So if we were doing like a left-hand limit, we would be coming from underneath. So these numbers right here look like the answer to this limit right here is basically saying that y is getting small. So the closer we get, see how that number is getting smaller and smaller? And that's the way that will always go. For a right-hand limit, you want to come from above. So as we get closer to 2, x is approaching 2 from the right, then your function values on this are getting bigger. So y is approaching positive infinity, like that. So if you kind of look at your graph on here, if this part on the right is going to positive infinity, the graph's going up forever, and then on the left side, it's going down to negative infinity like that. That's what the table says, and the answer to a limit can be written just as infinity or negative infinity. So what we'd have is our left-hand limit here. You can see on the table that one was going to negative infinity. The right-hand limit, you can see in my table, as I close in on 2 from the right, the numbers get bigger, so that would be positive infinity. And then what we've learned before is if the limits of the left and right hand are different, then this one does not exist. Okay? And you're more than welcome, again, to just put D and E as an abbreviation on that. Okay, so that's what happened. And anytime you have a vertical asymptote, you want to be solid on the concept that you're going to go to negative infinity or infinity. That's how vertical asymptotes behave on a rational function. They cause the graph to turn up and go to infinity or negative infinity. Okay, that's what we're going to look at. So that's what this definition is saying. You have a vertical asymptote. X equals A is a vertical asymptote if the graph either goes to infinity or negative infinity as x comes from the left or right on a limit. So that's what that's saying. Okay, so here's what I want you to do. First of all, I want you to just pause the video and just fill this out. I just want to fill this out. I really already answered that question, but just so that you're processing that, go ahead and fill that out. Okay, so here is what I hope you got. If you have a left-hand limit, then you're either going to go to negative infinity or positive infinity. Those are the only two possibilities there are. If you have a right-hand limit, it's exactly the same way. You're either going to get negative infinity or positive infinity. You won't get anything else. The graph won't stop and become some whole number around a vertical asymptote. If it's a two-sided, there's three choices. You can go to negative infinity, positive infinity, or does not exist. Okay, and does not exist would mean you have an asymptote, the left hand goes to infinity, the right hand goes to negative infinity. That would be the reason why it would exist, or would not exist. Okay? Okay, that's real important to do in this, is understand that if you're doing a limit near a vertical asymptote, your answer is negative infinity, infinity, or it could be does not exist on a two-sided limit. It can't be anything else. That's important to get in your head. Okay, so I'm going to have you go ahead and pause the video and go ahead and use your calculator to graph this function. Look at the table that I gave you and look at the graph to fill out what these three limits are. Okay? Okay. I have to play the guitar sometimes while I'm having you all do videos. All right. Or do problems, I mean. All right, so here's what we should have got. Let's go ahead and run through this and see if you got this okay. So I'll go ahead and put this in my graphing calculator. So I've got x minus 1 divided by x plus 3 to the second. Okay, and again, I'm just going to graph that in the same window I had. So what you're going to see on this one is your vertical asymptote comes here. You can figure out the vertical asymptote in your head. Usually it's pretty easy to do. Technically, you would do this. Take square root of both sides. You get x plus 3 equals 0. Solve the equation, so you get x equals negative 3. So that is the equation of your vertical asymptote then. All right. And again, what I'm going to do is I'm going to go to negative 3 and draw a vertical line and use dashes to represent that. And then the rest of this, you can get a few points if you see anything that's kind of a nice point. That's what I typically like to do, is just do that. So I see like a point negative 4, negative 5. That's kind of a nice point. I see negative 7, negative a half. That's kind of nice. I see negative 2, negative 3. And I see 1, 0. Like that, and that's probably good enough. So let's go and just kind of sketch it in. So what you have is a situation that kind of looks like this. Okay, the graph's getting close to the asymptote. And over on this side, it's turning down and going like that. And on this side, it actually goes a little bit above the x-axis, and then it approaches the x-axis like that. And that's a little hard to see, but if you traced some values, so like if you traced, say, at 5, well, see, you have a positive number, and it's going to stay positive forever. If you go down on your table of values, as x gets bigger, y just gets closer to 0, but it's always a positive number if you do that then. Okay, so here's basically what this is saying then. So the vertical asymptote is right here. That's your vertical asymptote. So your left-hand limit would be coming from underneath it like that. So if x goes to negative 3 from the left, then y gets smaller. See, it's getting smaller, so that's going to negative infinity. So your left-hand limit is going to be negative infinity. And you can tell that on the graph, it's going downward like that. Okay, your right-hand limit, you're coming from above, so you have x is approaching negative 3 from above. We'll look at the y values. The y values are doing the same thing. They're just getting smaller. So y is also going to negative infinity. All right. And then on this problem, since both the left and right hand limits are equal, then so is the two-sided limit. Okay. So that's hopefully what you got as your answer. So you want to know that if you're doing a limit at a vertical asymptote, you're going to get negative infinity or infinity for a left-hand limit. And it's also possible that the two-sided does not exist, but that didn't happen on this problem. Okay, very good. All right, so now we're going to kind of show you how to do this without graphing. You don't have to graph to figure this out. I'll show you kind of a simple way of doing this now. Okay, so at the bottom of the page, this kind of outlines the technique. It says if you're going to evaluate the left-hand limit. And we're talking about a vertical asymptote here. This is just a technique for if I'm asking you for a limit at a vertical asymptote. You pick a number that's a little bit to the left of the vertical asymptote, then you evaluate. And then if you're doing a right-hand limit, you pick a number to the right and then evaluate. So you're going to pick not test numbers that are really close. And one thing that you need to do is you don't have to use a calculator, but just use some decimal value that's very close to it. Okay, so I'll go to the next page and then I'll show you what I'm talking about here. So first of all, the first thing you have to do is you have to see that I'm asking for a limit at a vertical asymptote. And I am in this case. So this row right here has a vertical asymptote at x equals 9. That's what makes the denominator undefined. So since I'm asking for a limit at a vertical asymptote, you know your answers are going to be negative infinity or infinity for the one-sided limits. So here's what I'm going to do. All right, this one is a left-hand limit, so simply choose a number that's a little bit to the left of 9. I'm going to choose 8.9 as my test value. You don't want to use something like 0, although it would work on this problem. It's just a good rule of thumb to just use like a decimal that's real close. You don't have to use your calculator to calculate this anyway. So you're going to plug that into your function. So you get 8.9 plus 4 over 8.9 minus 9. Well, the numerator is positive, the denominator is negative, and we know a positive divided by a negative is a negative, so that means that the answer to that problem is negative infinity. That's all you got to do, is just see if you're getting a negative or positive value for your test point, okay? All right, the next one, okay, what we have is we have a right-hand limit. So what do? You choose a number a little bit to the right of 9. Yeah, you could use 10, but rule of thumb, just use a decimal, okay? Because you can do it in your head anyway. So what I'm going to do is plug it in. So I have 9.1 plus 4 over 9.1 minus 9. That's a positive over a positive. That's equal to a positive. That means the answer is positive infinity. Okay, that's how you know it. So you know the answer's got to be one of the two. You have a 50-50 chance of getting it right, see. Okay, so no test value is needed on this. Shouldn't even put that in there. That's not necessary. This would be does not exist, and the reason it does not exist is because these things are going in a different direction. So the answer to the left and right-hand limit are different. Okay, see, that's a real simple way to go through and do that without having to rely on graphing. Okay, let me do another one here, then I'll put you to work and you can do a few yourself here. Okay, first of all, on this one, you got to see that the vertical asymptote is at x equals 3. You can tell if x is 3, you have a 0 denominator. So that right there means, since I'm asking for the limit at the vertical asymptote, can't stress it enough, your answer is one of the two. You have a 50-50 chance of getting a one-sided limit correct. Okay, so test value. This is a left-hand limit. Use a number less than 3, like say 2.9. Okay, plug it in. If you plug this in, you're going to get 2.9 over 2.9 minus 3 to the second. So the numerator's positive. The denominator is a negative number squared, so that's positive over positive. Okay, so you get a positive result, so that means the answer of this problem is positive infinity. Okay? All right, so same idea, same thing works. Okay, the next one's a right-hand limit. So what are you going to use as a test value? I would say 3.1. Plug it in, and when you practice this, you start getting to a point where you can just kind of do this in your head anyway. You can just tell what the answer is if you imagine the test point in your head. So this would be 3.1 over 3.1 minus 3 squared. That's a positive numerator. That's a positive denominator. Therefore, you get positive infinity on that then. Okay? So, these are the same. So what's the answer to the two-sided limit? Since they're both the same, that will also be positive infinity. Okay, and again, no test value. You don't even need to show anything on that. You're just looking at, basing that conclusion on what happened on the left and right-hand limit. Okay, so that's an easy way to do this without graphing. So I'm going to go ahead and have you move down to the bottom of the page and do these next two problems. So I'm going to go ahead, and you can remember to pause the video anytime you need to. So I'm going to go ahead and move down here and go ahead and work these problems out. And as soon as you're ready to check, resume the video. Okay, so here's what you should have did. And let's see, the first problem number 1, you would get the left-hand limit, negative infinity, right-hand limit, positive infinity, does not exist. Number 2, the left hand would be positive infinity, right hand is negative infinity, so again, the two-sided does not exist. So you want to kind of see how I did test points, how I did my arithmetic. And again, sometimes students don't like using decimals. And most of the time you're okay if you use a whole number. But if you use a whole number that's passed on the other side of another vertical asymptote, it's going to mess you up. So I just recommend using decimals. And I added in on here the graph, so you can kind of see on this number 1, this is what the graph looks like. So you can see the left hand goes to negative infinity, the right goes to infinity. And on number 2, you can see that the left hand limit goes to infinity, and the right hand goes to negative infinity like that. Okay, so that's how that everything works out. Okay, so that is it for that. So that'll kind of help us with asymptotes, vertical asymptotes for now. Okay, so I'm going to move the next page. I'm going to go ahead and do one more example of this, and then that will be the end of the first part of the video. The first part of the video is going to talk about limits at a vertical asymptote. So we call these infinite limits because their answers are at infinity or negative infinity. This is another situation where you get a deleted point or a hole, and you have a 0 over 0 form on your limit on this. So first of all, what we need to do on this problem is you want to go ahead and factor this. So I've got f of x. I'm going to go ahead and factor that numerator. So I'm going to draw 2 parentheses. X times x, of course, is the first term. 2 numbers that multiply to give 6. You could have 1 and 6. You could have 2 times 3. 2 and 3 is the correct choice because you're trying to make the inner term add up to negative 1. So negative 3 and positive 2 add up to negative 1. So that's how that cancels. That's how that combines. So that's bottom is x plus 3, x minus 3, because that's a difference of 2 squares. Okay, so what do you have on this then? Well, okay, this one gives the whole, because this one cancels out. So you have a whole at x minus 3 equals 0, or you have it at x equals 3. So just write the answer to your whole, that's at x equals 3. You don't want to put a point there because you're undefined there. There's not a defined point there. It's just when x is equal to 3, you have a hole in the graph. Okay, the one that's left over, this one is your vertical asymptote. So your vertical asymptote is found by thinking of this equation. So your vertical asymptote is x equals negative 3. Okay, so that's how we're going to start the problem, is you want to figure out where the hole is, and then you want to figure out where the vertical asymptote is. So that's how that goes. The one that cancels is the hole. The one that's left over is the vertical asymptote. So what I'm going to do on this then is we'll go ahead and we're going to put the vertical asymptote on here. So go to negative 3, and then draw your vertical line through x equals negative 3 like that. And then we're going to do this on the graphing calculator, and I'll show you what happens on this then. Okay, so I'm going to put the original in now. I want to put the original in, not the not the version after the x minus 3 cancels. So we're going to put in x squared minus x minus 6, and then divide by, and then we'll have x squared minus 9, like that. And again, I'll do that in the standard window. So you're already going to see that you have your vertical asymptote here, okay, like that, and the hole is at 3. Now it's hard to see on here. You just usually, unless you really zoom in, you aren't going to see those things. Like if I changed my window to like negative 3 to 3, or no, let's say negative 3 to 4 on the x-axis, I still can't really see it. Sometimes you'll be able to see a break in there, but the graphing calculator is not always kind enough to tell you where that hole is. You have to figure that out yourself. Again, you're going to see on here that if you just scroll through your values, that's your asymptote right there. And then the other one where you have an error is at 3. So there are 2 places this function's undefined. Okay, so I'm going to go to my table of values, and again, like I'm used to doing, I'll just find a few good points. I see like -4, 2. I like that one. And then I see -2, 0. I like that one. I've got -1 and 0.5. And that's probably, good enough. So you have -1 and then 0.5. And that'll be good enough. Because all I'm going to do on this is just kind of have you sketch your graph anyway. So that's going to go up. That's going to go down. And then part of the graph will go like this. And what will happen is this, we'll talk about horizontal asymptotes. This thing right here is really going to level off at y = 1. And we'll talk in a little bit about why that is. So let me show you how to do this without the assistance of your graphing calculator. We're going to use test points on this, but what we're going to do is we're going to use this thing to plug our test points in. Okay, because it just makes it simpler to do it this way. So this is a left-hand limit. We're doing the left-hand limit at a vertical asymptote. So I'm going to choose as my test point. Let's just use something like negative, and you could use -4. I mean, I'm going to just go ahead and use -3.1. And then I plug into what I highlighted in blue. I have -3.1 plus 2 over -3.1 plus 3. So that is a negative over a negative, which is a positive. That means the answer to that limit's positive infinity. Now you can tell by your graph visually that if you're on the left-hand side of the asymptote, that graph is going up to positive infinity. Okay, so that's how you can work that out. The next one is a right-hand limit, so let's use as our test point, let's use -2.9. Again, plug into not the thing, the square and all that. Keep it simple. Plug into the reduced form. So we'll have -2.9 plus 2 over -2.9 plus 3. That is a negative over a positive. Therefore, that's a negative. So that means we get negative infinity as our answer there. Okay? And what you're going to know from this then is you can pretty well tell that on the graph. It's pretty clear that thing is going to negative infinity from the right. And then this does not exist because the left and right hand limit are going to different places. All right, so that's how that goes. All right, so that is the vertical asymptote. Vertical asymptote use test points. Now, on a hole, this next row is at the hole. On a hole, don't use test points. Just plug the number in. Okay, so again, this really turns out to be the same. This problem right here is the same as the limit as x goes to 3 from the left of x plus 2 over x plus 3. So plug it in. And you're not going to get anything undefined. You're going to get a numeric answer. So what you'll have on here is that will be 3 plus 2 over 3 plus 3. So that's going to be 5 over 6. So that's what that limit is. Okay? All right. Now what's going to happen is you're going to get the same answer on all these. Okay? Because you're going to go to the same place. You're still going to plug that number in. So when you do this next one, that's also 5 over 6. Because you're just doing the limit x goes to 3 from the right of x plus 2 over x plus 3. You're just repeating yourself. And then the two-sided limit will be the same as well. And see what happens on your graph, you can tell if x is equal to 3, you have this hole here. So the left and right-hand limit are both going to the same place. Okay? Another thing I want to mention on this is, well, you can tell you're right. Again, you can kind of go back to the techniques we learned. If I trace at 3 on this, Okay, well, I'm undefined at 3. That's where my hole is. But if I use something like 2.99999, something real close to 3, well, that thing right there is close to 0.83. And what I want you to notice on this is you can check your answer just by doing this on the calculator. You can just take your calculator now and do this. Okay, so if I take 5/6 and just see what that decimal is. See that well, I put the wrong thing in. What's wrong with me? 5 divided by 6. Okay, I put that in. It's 0.83333. See how it matches? So those things match. And that's how you can tell you've done that right. Okay? All right. So that will be the end of part 1 of the video. And that will get you through how to work with a limit at a vertical asymptote. Okay, hope you enjoyed the video. And good luck to you. Let me know if you have any questions or need any help.